Welcome back to Math 168 and another thrilling episode in our lecture sequence. This is section 2.1. This is descriptive statistics, and it's the first step in analyzing and looking at descriptive statistics. So what do we actually mean when we talk about a descriptive statistic? Let me get rid of myself so I can make a little more room here. So as an outline or as a starting place here, let's talk about categorical data. Remember that if we have one categorical data, sometimes we call that 1C, the summary statistic is a frequency table, and from a frequency table we draw a single proportion. So that is a statistic which we would use to analyze a one categorical situation. For visualization of that, we'd use a bar chart or a pie chart. So always goes along with a single categorical. If we have two categoricals, well, then the summary statistic is going to be two-way tables, not just simply a frequency table, but now we have to have two different categories and have frequency for both of them, and that's when we describe it as a two-way table. Instead of a single proportion, we're going to look at the difference in proportions, and the visualization will change from a bar chart to a segmented bar chart, and instead of a pie chart, we'll utilize a side-by-side chart. Again, this is categorical data. So in the big picture, remember what we're shooting for here is that from a population, we're going to take a sampling. And when we take that sampling, we're going to pull a descriptive statistic, some kind of number to discuss. And since we're in categorical, that's going to be a proportion value that we're going to pull from that sample data. And from there, we're going to make some statistical inference about the population based on that descriptive statistic that was pulled from that sample. So in descriptive statistics, in order to make sense of this, we have to summarize it and we have to visualize it. To summarize it, we'll use a descriptive statistic variable. And to visualize it, we'll use one of the charts that we were speaking of. When we summarize a visualization variable, the relationship between it, it's often called the descriptive statistic. For instance, the p-hat value, which is a descriptive statistic for a single categorization, is the descriptive statistic. It says it's also known as the exploratory data analysis, but descriptive statistic is pretty often used. The type of summary statistic and the visualization method clearly is defined by whether you have categorical, quantitative, or a mixture of the two things, and how many of them you actually have. For instance, this one categorical data that we're speaking of. If we were to build and this is a random sampling of US adults from 2012 who own cell phones, this is a frequency table. A frequency table simply shows a type of category, so a single category, and the tally number or the number of the values for each one. So an Android was 458, a BlackBerry was 141, and no cell phone was 293. The total of all were 2253. Now, if we take that frequency table and we turn it into a proportion is a p-hat value, as you see stated below, for a sample. For a proportion, it's a population, or p. The proportion is the category found by taking the number in the category and dividing it by the total sample size. For example, if we wanted to calculate the number of no cell phone users, that would be a p-hat, because that is the proportion of a sample. 293 out of 2253 would return a 0.13, or approximate 13%. Proportions and percentages can be used interchangeably. The majority of the time, we will always use the decimal value. So we want to stick to decimals rather than the percents, but we'll use the percents in order to explain things. In a relative frequency table, all the data comes from the original table that you saw. So this original frequency table here is now referred to as a relative frequency table when we actually do all of those p-hat values and put the decimals in place. So you can see that 0.130 was inserted for the no cell phone. In order to calculate the non-smartphone, we take the relative frequency of that value. And that would have been, for non-smartphone, would have been 924 divided by 2253. The BlackBerry would have been 141 divided by 2253. The iPhone would have been 437 divided by 2253. And lastly, the Android 458. All of the relative frequencies have to add up to be 1. Because remember, if these are percentages, it has to account for 100%. And 100% is the same as 1.00. Here goes a question that's in Wiley. And we'll take a look at this question quickly. This exercise provides information about data in a survey. Of the students who identified their class year in a survey, 121 of them were first year. So that's an important piece of information. And I'm jotting down 121 out of first year. 213 of them were sophomore. Again, I'm jotting that down. 64 of them were junior. And 46 of them were senior. If I were just simply building a table, that would be the likes of my table. I would have my categories, and I would have my frequency in which they occurred. Find the p-hat proportion who are upper class students, that is, those who are juniors or seniors. Okay, so if I go back to finding that p-hat value for upper, and we find the juniors are 64, and we find the seniors who are 46, and of all of these, we have to have a sum of all, and I don't remember the sum of these values, and we'll have to get them. So first of all, we'll get our 64 and our 46. And we could do this all in one calculation, but we'll just take it off the side. So we get 110 juniors and seniors. Now we need to take that 110 and we need to add to it the remainder, which were the 213 sophomores, plus the 121 first years, 444. And in order to get the relative frequency, we'll take 110 and we'll divide it by 444. And we'll get approximately 248 if we round to 3 positions. P hat is 0.248. When it said, and I got lucky, it said round your answer to 3 decimal places. Moving on to the next one. So a bar chart, sorry, a little too high there. A bar chart, a plot, a graph. We use a bar chart in order to see a single categorical piece of data. You notice across the bottom of the bar chart, and I'm going to put a little bit of drawing down here. Across the bottom are all the categories. And going up the sides are just simply the counts. So if we look at the BlackBerry, it corresponded to a count that's something under 200, but yet something over 100. All the bar chart does is show the count in each one. You would have known this as a bar graph for your entire life. You can also use a pie chart, and a pie chart is a perfectly good way of showing what the data is and what percentage is in each one. So if we're looking for the proportion percentage, instead of just physically the count, like here, then we would use a pie chart. Now remember, this is only for single categorical data. Once we go outside of single categorical data, then it's not going to work. StatKey also does this very same thing. It shows descriptive statistics for one categorical data. If I jumped over to StatKey real fast, and I looked at single categorical data, right here, one categorical. My internet is dragging a little bit right here. So you can see that a bar chart shows the count that I have for this. It won't show me the circle graph, but we could make a circle graph pretty quickly. Notice that the statistics over here to the right-hand side show the count and the proportion as well. So not only do they show the frequency, but they show the relative frequencies. Summarize. One categorical variables. They use a proportion, they use a frequency table, and they use a relative frequency table for their summary statistic. Their visualization is a bar chart or a pie chart. Posted inside of your textbook, your electronic textbook that's online, you can see something very similar to this in Table 1A. And I'll post this for you online also inside of Canvas. It does a nice job of this. It lays out one categorical, bar chart, pie chart, a proportion, a frequency table, and a relative frequency table. You can see that we're going to go on to do other items at the same time. So again, I will post that for you in Canvas. So let's talk two categorical variables. Two categorical variables is a relationship between two different categories. So in this two-way table, we have categoricals across the top, male, female. But yet at the same time, we have another category, relationship, complicated, single, and we have a total row. So the two-way is the two different categories within the measurements that we're looking. The frequency count is still taking place, but now we have a total of those frequencies for not only the rows, but the columns and the total. Down here, 169 is the total for the entire set, whereas 108 is the row total for being single, and the male total is 62. It says it does not matter which variable is displayed in a row and which one is displayed in a column. So we have a couple of questions here about a two-way table. So the first question is, what proportion of students are in a relationship? So a couple of things we have to look at. So first of all, what proportion of students? We need to identify who we're talking about here. And who we're talking about are of students. There are 169 students. There are 42 of them who are actually in a relationship. So when I'm looking at a p-hat value for what we're speaking of, we're finding the intersection for number one. We're finding the p-hat value of the numerator, those in a relationship, compared to all of the students, those in the group, because it said of students. And when we do that division, let me do the math. 42 divided by 169, approximately 0.25 if we round to two decimals. And it doesn't say what to round to, so I'm just going to go with 2. There's the approximation for p-hat for number one for what proportion of students are in a relationship. Let's go to the next one. What proportion of females? Okay, so now it's not of all, now it's simply of females. Well, of females, the total of those are 107. How many of those are in a relationship? Well, 32. So when I do the calculations for here, for number 2, the p-hat value is going to be 32 out of 107. And again, if I do that division and I do my rounding, 0.3. Let's go find number 3. What proportion of students, what proportion of students in a relationship? Okay, so be careful here. It's not just of students, it's of students in a relationship. So if I look at students in a relationship, that's 42. How many of those are actually female? Okay, well, that's 32. So now my calculation for the p-hat value for number 3, and remember, the p-hat means my proportion of the sample, is 32 out of 42 for 0.76. Drastically changes with the wording of who is the entire population that I'm looking at. What proportion of males, okay, so it's of males, are in a relationship? Okay, well, there are 62 males, and of them, 10 are in a relationship. So my p-hat calculation for number 4 is 10 are in the relationship out of 62 actual males for 0.16. It says caution, the proportion of females in a relationship is not the same as the proportion of people in a relationship. If you go back to what we took a look at, that was these two numbers here. That was 30% versus 76%. And if you look at the wording was very close. Proportion of females are in a relationship, proportion of students in a relationship that are female. These are not the same thing, obviously, because they carry a completely different percentage. When you look at the male and the female proportions, 30% of the females in the sample say they are actually in a relationship. And 16% of the males sampled say they are in a relationship. It says, why the difference? Well, why the difference is why we're here. We're here to look at when we have two different groups that are using a proportion for an analysis of their data. The difference of proportions becomes that value that we're talking about. If I go back to that little chart I showed you a minute ago, if I have two categorical pieces of data, then a two-way table and a difference in proportion is the summary statistic that we utilize. So my summary statistic becomes a difference of two proportions because I have a 30% and I have a 16% for two different categories that I'm looking at. It says we calculate the difference for the different levels of other category variables and the parameter of interest for two categorical variables. We'll use that wording right there pretty frequently. Parameter of interest. And the parameter of interest is the measurement for the population. And the population parameter of interest for two categoricals is a proportion because you're using a sample. A sample is the p-hat value that goes along with that proportion. Example, a proportion of females in a relationship minus the proportion of males in a relationship. So p-hat of female minus p-hat of male is 30 minus 0.16, which means that the statistic that we are looking at, there we go, 0.14. This is my statistic of interest. Difference in proportions. So the question says that we should find, well, first of all, we have all of those same particular values right there. And it says that we should find the difference in proportions for P or p-hat of R minus p-hat of S. P-hat of R stands for the proportion of students in a relationship who are female. Okay, so let's go find some stuff that we need to have first of all. And let's grab a color here. So let's do this first one. So we're looking for the proportion of students in a relationship. Okay, well, when I look at students who are actually in a relationship, that's 42 students. And of those, how many of them are actually female? So we're looking at female, so we're getting that 32 out of 42. Okay, so first of all, if I jump over here, my p hat of R, because that's what it was given to be, is 32 out of 42 for approximately 0.762. My second calculation is the proportion of single students. Okay, so I go to single students, that's 108, who are female, and that's going to be 63. So my p-hat value of S is 63 out of 108 for 0.583. What they want me to calculate is right here. They want P of R minus P of S. So p-hat of R minus p-hat of S. Okay, so p-hat of R minus p-hat of S is equal to 0.762 minus 0.583. My statistic of interest is not either one of these. My statistic of interest is 0.179. This is my statistic of interest. May be careful here And I probably should write this down for you. Let me type it in here. Order matters. If I change it around into p hat of s minus p hat of r, the statistic would be completely different. It'd be negative 0.179, which would make a huge difference. If we're looking at a segmented bar chart, it's just like a side-by-side bar chart, but the bars are stacked instead of being side by side. So these are the relationships in a relationship. The darker one is female and the lighter one is male. So we can see the difference in any category of the secondary category. Because remember, this is two categorical data. Side by side looks almost identical. And here's a stack, which gives exactly the same data as being side by side. Both of them have corresponding values that come from the two-way table. This is one I think we can probably do this. So I would encourage you to take a moment, stall, read it, and then come back to me, and then we'll start finding important information here. Okay, so hopefully you took a look at it, and here's what it says. It says that if we have learned to problem solve by one method, we often have difficulty bringing in new insight to similar problems. However, electrical stimulation of the brain appears to help subjects come up with fresh insight. In a recent experiment conducted at the University of Sydney in Australia, 40 participants, okay, so that's important. I'm going to do a little highlighting while we're here. Let's go with this. So 40 participants were trained to solve problems in a certain way and then asked to solve an unfamiliar problem that required fresh insight. Half, that's important, so 20, half of the participants were randomly assigned to receive non-invasive electrical stimulation of the brain. Great. While the other half, the control group, received a sham stimulation. Remember, the control group never gets anything. They have the placebo. So far we have 40, and we have half of them in each group. The participants did not know which group they were in. In the control group, 20% of the participants successfully solved the problem, while 60% of the participants who received the brain stimulation solved theirs. So we have a success rate of 20% in the control group, and we have a success rate of 60% in the other group. So let's go down and see what our questions are here. Is this an experiment or is this an observation? Well, obviously this is an experiment because we have two different control group. We have a control group, and we are putting people into groups and giving them electrical stimulation. Does it appear that this study is single, double, or no blind? Well, it appears it's single because it says the participants did not know. It didn't say anything about the observers knowing or not. So now we have to go get some numbers here, and we got to figure some things out. Well, first of all, we know, and let me get a text box happening here. We know that there's 40 people in the entire group. We also know that there's 20 in each subgroup. Oops, sorry. We know there's 20 in each of the subgroups. Let me go back to my text box. There's 20 in this group, and there's 20 in this group because it says they were split in half. So now what we have to figure out is, okay, how many are in these? Well, the key is going to come from this successful box right here. It's told us that 60% of those in one group, that's 60% or 0.6 of 20 were successful in the brain stimulation one. Well, 60% of 20 is 12. And it said that 20% of the other group, which was also 20, were successful who did not receive the placebo group, and they were 4, or 20% of 20 is 4. So if I go back now and I do a little bit more typing here, that means under electrical stimulation, right here, 12 were successful. And that means here, 4 were successful. Now, in order to get my not successful, well, obviously it's going to be 20 minus the 12, which means in this particular category, I'm going to have 8. I would do exactly the same thing here. I would take my 20, I would minus my given 4, and I'd be equal to 16. My totals, I could just simply add 12 and 4. 12 and 4 makes 16. And for my other one, 16 and 8 makes 24. So I have my values that I need in order to do my percentages. Next question. What percentage of people who correctly solve the problem? Okay, so first of all, you look at those who correctly solved a problem, right here, successfully solved a problem, which is 16. How many of those had electrical stimulation? Okay, well, those had electrical stimulation, it was 12. So we would do a p hat value here. We do a p hat, and p hat would be 12 of 16. And 12 of 16 is approximately 0.75. Not approximately, actually, 0.75. So it's 0.75. And p hat equals 0.75. Give values of P of E. Give values of P of E. So this is the percentile of electric, the proportion of people in the electrical stimulation group, and P of S, the proportion of people in the sham stimulation group, to solve the problem. What is the difference between P of E and P of S? All right, well, now it's talking about P of E, the proportion of people in the electrical stimulation group. So the number of people in the electrical stimulation group was 12 out of 20. The number in the placebo group was 4 out of 20. So we're going to want to make a calculation here in order to see that. So my P of E is going to be 12 out of 20. My P of S, my other group, is going to be 4 out of 20. And they want us to calculate P of E, P hat of E, minus P hat of S. So really, it's 12 out of 20 minus 4 out of 20, which is equal to 8 out of 20. And when you divide 8 out of 20, it's going to be 40. 0.4. So go back to my value. What is the calculation for the statistic? 0.4 or 40%. Letter F. Does electrical stimulation of the brain appear to help insight? Why? Well, the answer is going to be yes. Question why? Well, first of all, we had a 40% difference in those who received stimulation and those who did not receive stimulation, which was a huge value. In addition to that, those who were in the electrical stimulation group, 75% of them solved the problem successfully out of just that group. So we had two pieces of data. One, 75% success, and two, 40% increase compared to the placebo group. We also could have a discussion about how this is it's a valid test. It's not an observation, and we could actually put a little bit of causation here. So yes, electrical stim does help people. Does help people. Oops, can't type. People gain insight, and it would be on new problem solving. I wouldn't go trying this on yourself. Okay, I think that to summarize, two categorical variables. We'll use a summary statistic, which comes from a two-way table. We will talk about the difference in proportions. The visualization for that is a side-by-side bar chart or a segmented bar chart. That concludes chapter 2.1. When you come back, we'll be moving right along in chapter 2.2. Nice seeing you again.